Welcome to Lesson 17, Special Right Triangles. This is the beginning of our unit on trigonometry. Trigonometry means triangle measure, so it is literally the study of the measure of triangles. At the beginning of your notes, add this information as there is no place later in your notes to put it. It is important to know that if you start with a right triangle and you drop an altitude from the right angle of the right triangle to the hypotenuse, you will create three similar triangles. This is an important property to know that is often used to solve problems. In this particular case, we see that triangle ABC is similar to triangle ADC, which is similar to triangle BDC. Remember that figures which are similar share the same angle measures but different length sides, and their sides are proportional. It is always important to label the right triangles that are similar so that the corresponding angles are matched up in the naming. On the next page of your notes, underneath the objectives, we're going to add some more information. Today we're going to talk about two particular special right triangles. The first one is called a 45-45-90 triangle. And this is a triangle in which it is a right triangle and therefore has a 90-degree angle, and it is isosceles. Because it's isosceles, the other two angles are each 45 degrees. If you know the leg of a 45-45-90 right triangle, you can find the hypotenuse by multiplying the leg by the square root of 2. So in this particular example, we have indicated that the length of the leg is x, and therefore the hypotenuse would be x times the square root of 2. So given any leg length, in order to find the hypotenuse, you take the leg and you multiply by the square root of 2. The other type of problem you will frequently encounter is a situation in which you know the hypotenuse, and instead of finding the hypotenuse, you need to find a leg. So you would simply divide the hypotenuse by the square root of 2. So to find the leg, you do hypotenuse divided by the square root of 2. We will do some examples later that will hopefully make more sense. The other special right triangle is the 30-60-90 right triangle. In this particular case, we have a right triangle which has angles that are 30 and 60 degrees. These sides of the triangles also have a special relationship. If you know the short leg, and this would be the leg between the 90 and 60 degree angles, you can find the hypotenuse of the triangle by simply multiplying by 2. So to find the hypotenuse, you do the short leg times 2. If you'd like to find the length of the long leg, you would multiply the short leg by the square root of 3, as indicated here. Long equals the short leg times the square root of 3. Sometimes you're given either the hypotenuse or the long leg, and you need to find the short leg. In order to find the short leg, you can divide the hypotenuse by 2, or divide the long leg by the square root of 3. And both of those equations are indicated here. As we mentioned, these two particular triangles have a special name. You will want to jot down the vocabulary here. A 45-45-90 is just as it sounds, a triangle with angles of 45, 45, and 90 degrees. And similarly, a 30-60-90 triangle is a triangle with angles of 30, 60, and 90 degrees. To look further at the special properties of a 45-40-90, we only need to consider the Pythagorean theorem. Remember that the Pythagorean theorem tells us that c squared, with c being the hypotenuse of a right triangle, equals a squared plus b squared. If I were to start with a figure that were a perfect square and therefore had a 90-degree angle in the corner, both sides of the square could be labeled x. If we consider the diagonal that goes across the square as the hypotenuse, or h, of a right triangle, we could substitute h for c and x for a as well as x for b, because in this right triangle, the two legs are the same length. Therefore, we get h squared equals x squared plus x squared. That simplifies to h squared equals 2x squared. To find h, we need to take the square root of both sides. And in doing so, we find that the square root of 2x squared is x times the square root of 2. So therefore, the hypotenuse equals x, or the length of a leg, times the square root of 2. That's why it works. A common problem that you might find this time of year would be one regarding baseball. On a baseball diamond, the distance from home plate to first base is 90 degrees. What's the distance from home plate to third base? Since a baseball diamond is actually a square, the distance from home base to third is also 90 degrees. The question is, how far does a player have to throw a ball to get it from first base over to third base? So again, this is like our Pythagorean theorem example above. We have a square in which we are drawing a diagonal. In this case, I happen to know that each of the legs is 90 degrees. So in order to find the hypotenuse, which would be the distance between first and third base, I would multiply 90 times the square root of 2, which comes out to 127 feet. So that's the distance that a player would have to be able to throw the ball between first and third base. In our next example, we're given an isosceles triangle, an isosceles right triangle. As soon as I hear isosceles and right together, in my mind it should click that this must be a 45, 45, 90 right triangle. It says that the legs are 60 feet long, and the question is, how long is the hypotenuse? So keeping in mind that the hypotenuse is always the leg times the square root of 2, then the hypotenuse of this triangle would be 60 times the square root of 2. If I'm given an isosceles right triangle, and in this case I know that the hypotenuse is 17, and I would like to find the length of each leg, I can start off with a similar equation, plug in 17 for the hypotenuse because that's what I know. I don't know the leg, but I know that it has to be multiplied by the square root of 2. So in order to simplify, I would divide both sides of the equation by the square root of 2, and I would find that the leg is 17 divided by the square root of 2, which is 12. In our next example, we're going to look at a 30, 60, 90 triangle. In this case, as we mentioned earlier, the hypotenuse is twice as long as the short leg, and the long leg is the square root of 3 times the short leg. So in this particular example, if my short leg is x, my hypotenuse would be 2x, and the long leg would be x square roots of 3. Looking at example 4 below, I am asked to solve for x and y. So keep in mind that y, the short leg, will be half the length of the hypotenuse. Therefore, y must equal 18 divided by 2, or 9. Once I know that the short leg is 9, then in order to find the long leg, I would simply do 9 times the square root of 3. And in this case, that comes out to be approximately 15.6 units. In example 5, I am given an equilateral triangle, 60, 60, and 60 degrees, and an altitude has been dropped, which creates a 90-degree angle at the center of the base of the triangle, which tells me that I now have a 60-degree angle, a 90-degree angle, and a 30-degree angle. So therefore, I can apply all the things I know about 30, 60, 90 right triangles. In order to find y, which is labeled over here, but keep in mind that these two pieces are congruent because this altitude actually bisects the base, I know that y will equal the hypotenuse divided by 2. So I have 9 divided by 2, or y will equal 4.5 units. In order to find x, which has become the long leg of the triangle, I would multiply the short leg, 4.5, times the square root of 3. So x will equal 4.5 times the square root of 3. And this comes out to be approximately 7.8 units. I hope that these examples will help you to solve special right triangle problems.